All right, in this last video for this module, we're going to be talking about capacitors, what they're used for, and working some problems with changes in energy regarding capacitors. Now, I linked you to a video that I thought did an excellent job in explaining exactly how capacitors work. Basically, you've got two parallel plates. You've got one of those plates carries a negative charge, one of them carries a positive charge. And what we generally use them for most often is to accelerate particles, charged particles in between them. The author of your textbook gives you this particular equation, V equals Q over C sub Q, where V is the electric potential, just like it always has been before. The Q in this is the positive charge in the capacitor. Now, as you can tell from the video that you saw, the positive charge and the negative charge are going to be equal in magnitude, but they're going to be opposite in charge. And then the capacitance of the capacitor is in farads or in coulombs per volt. That's what a farad actually is a coulomb per volt. And so basically what that is, it's a value that depends on the specific capacitor that you're using. And it tells you how much charge it is able to hold at a given voltage. Now, he does not go into, he explains it, but he doesn't go into a lot of detail about it. The video did, and so what I do expect you to be able to understand how you can actually increase the amount of charge that a capacitor can hold. And the video talked about really 3 different ways that you could do that. They said that you could increase the charge that a capacitor can hold by decreasing the distance between the plates, because when you decrease the distance between them, the force is going to be greater, and so therefore you're going to be able to accelerate the particles more quickly. So you can decrease the distance between the plates. You can put a conductive material between the plates. In the capacitor that you built, you just had air in between your 2 plates, and a lot of capacitors just have air in them, but you can put an additional conductive material between them to cause them to be able to hold more charge. Or the third thing you can do is you can just increase the size of the plates, because the bigger the plates are, the more charge that they're able to hold. So like I said, I do expect you to know these 3 points, so if you want to jot those down, that might be a good idea. Okay? Excuse me. So the other thing that he specifically mentions that you need to keep in track of in your head is that if a particle goes from a negative plate to the positive plate, the electric potential is going to go up. And if a particle goes from a positive plate to the negative plate, the electric potential is going to go down. Okay, now you can remember that actually pretty easily, because if you're going from like a negative number to a positive number, the value of the number goes up. If you're going from a positive number to a negative number, the value of your number goes down. So you can, that's actually something that's pretty easy to remember. So that's something that you want to kind of stick in the back of your head as you're working these problems as well. So we are going to work example 14.6. So let me get rid of this so that we have room to work this problem. And once you've worked all of the other problems that involve potential and kinetic energy, this is really kind of more of the same. So we're going to try to get all this information up here. You have a freely moving electron where the mass is 9.1 times 10 to the minus 31st kilograms. They give you the charge on that electron. It starts at rest and it travels from the negative plate to the positive plate in this capacitor, and it wants to know how fast it will be moving once that happens. So once again, I just want to draw a picture because I think it will help you see what's going on. So if you have a capacitor, and I'm going to put the negative plate up here at the top, and I'm going to put the positive plate down here at the bottom, and it tells us that we have an electron, and it's going to travel from the negative plate to the positive plate. Now, that makes sense because an electron has a negative charge. Negative charges repel each other, and so that negative charge is going to be attracted to the positive plate. So yes, obviously it's going to want to travel that direction. So we know the mass of that charge We know the amount of the charge. We know the capacitance of the capacitor itself, and we know what the how much stored charge it has. So once we know all of those things, then we're able to actually calculate the velocity. So how do we go about doing that? Well, if you know this equation right here, Q over C sub Q, we can then calculate what the electric potential is of this particular capacitor. So we know that the charge that it can hold is 5.5 times 10 to the minus 4th coulombs, because it tells you that that's what the charge on the stored charge is. It says it's 0.55 millicoulombs, and that's, which is 5.5 times 10 to the minus 4 coulombs. It also then gives us the capacitance of the capacitor, and that is 3.1 times 10 to the minus 6 farads. Farads. And you already know then, because you should have already seen this, that a farad is the same as a coulomb per volt. And so that means that these coulombs will cancel out, and so you're going to end up with volts. And so that should be normal, because that's what electric potential should be measured in volts. So that's going to give me 1.8 times 10 to the second volts. Okay, now which direction is it going? Well, it's going from the negative plate to the positive plate, and so that's a positive change, and so therefore that delta V is going to have a positive number on it. Once I know the V, I can then calculate the potential energy that that particle is going to experience using this equation. So potential energy is going to be equal to the charge on the electron, which is 1.6 times 10 to the minus 19th coulombs, and it is negative because it is an electron. And then I calculated this V from up here, 1.8 times 10 to the second volts. And when I crunch those numbers, it will give me negative 2.9 times 10 to the minus 17th joules. Okay, potential energy in joules, just like it was before. Okay, now, therefore, does that make sense? Well, yeah, it should, because what's this particle doing? It's accelerating. It's going from a negative plate and it's moving to the positive plate. So that means that my kinetic energy is increasing. And so if my kinetic energy is increasing, the potential energy should be decreasing. So that negative sign makes sense. Okay, so if the potential energy is decreasing, the kinetic energy is going to increase by the same amount. And so therefore, this was negative before because the potential energy is decreasing. So this is going to increase 2.9 times 10 to the negative 17th joules equals 1/2. The mass of the electron is 9.1 times 10 to the minus 31st kilograms. And then I can then solve that for V squared, or I can solve it for V. And so what I'm going to end up with is an amazing speed of 8.0 times 10 to the 6th meters per second, okay? So really the only thing new in this particular type of problem is that in order to calculate the V, you've got to take into account the information about the specific capacitor in order to calculate that V. Okay, and the potential difference is the potential difference between the plates, and that's where the particles are moving between, is between the two plates.